Hello. In this video, I'll show you how Bitcoin works. I'll present all the main ideas, but I will make some simplifications in order to keep the presentation short. I hope you get the sense that the ideas behind Bitcoin are all extremely simple and elegant. However, they are extremely powerful. I'll begin by highlighting the main elements of Bitcoin. These will be described in more detail later in this video. A transaction is a transferring of a coin from one user to another. Since Bitcoin is decentralized, there is no single party who can attest to the validity of a Bitcoin transaction. And so all transactions must be public and broadcast to all users. This broadcast takes place via a peer-to-peer network called the Bitcoin network. Anyone can join this network. Every 10 minutes or so, the latest transactions are verified and collected in a block. This block is hashed and cryptographically linked with the previous block. The block is then broadcast to everyone via the peer-to-peer network. The list of blocks is called a blockchain. It contains a record of all past transactions. We will see that the blockchain has the properties of being public, having consensus, liveliness, and persistence. The verifying of transactions and compiling of a block is called mining. This is done by volunteers called miners. In order to incentivize volunteers to mine, a miner receives a reward, which is R bitcoins for each block that they mine. The miner must do some work in order to receive this reward. This work is the solution of the cryptographic challenge. Once this work is done, it can be verified anyone using the proof of work. The very first bitcoins were generated by Satoshi Nakamoto on the 3rd of January 2009. This generation was in the form of a declaration, namely that Satoshi, who was identified by his ECDSA public key S, is granted 50 bitcoins. This transaction is called T0, the Genesis transaction. So you can see that these bitcoins have no intrinsic value. They are simply a declaration that Satoshi has 50 bitcoins. The bitcoins eventually gain value as other people begin to use bitcoins and trade it for goods, services, or for other currencies. The first block in the Bitcoin blockchain was also created by Satoshi Nakamoto on the 3rd of January 2009. It is called Block 0, the Genesis block. Block 0 contains a transaction T0 and Satoshi's public key S. It also contains a nonce selected by Satoshi so that the SHA-256 of the block 0 begins with a prescribed number of zeros. Block 0 is embedded in the Bitcoin software, and so when a user downloads an authentic copy of the Bitcoin software, the user obtains an authentic copy of block 0. Okay, so that describes the first bitcoins and the first block in the Bitcoin blockchain. We need to ask the following questions now. How are new bitcoins minted? How can someone spend a bitcoin in a transaction? In other words, how does Alice give a coin to Bob? How can one verify that a transaction is valid? In other words, how does Bob verify that the spender Alice actually owns the coin and has not already spent the coin? And the last question is, how is the blockchain updated while maintaining the properties of being readable by everyone, agreeable by everyone, writable by everyone, and changeable by no one? I will answer these questions in the next few slides. Every Bitcoin user has an ECDSA public-private key pair. In fact, the user could have many such public-private key pairs. The private key will be denoted by a small letter, so A, B, or C, and the corresponding public key by the corresponding capital letter, capital A, capital B, or capital C. The Bitcoin blockchain does not record the names of people involved in transactions, but instead records their public keys. So a user's public key, A for example, serves as a pseudonym for that user. More generally, a user can select a different key pair for each of her transactions. This can give the user a degree of anonymity when she spends her Bitcoin, provided that she exercises some care. A transaction is a transfer of a coin from one user to another. Suppose that Alice has a coin, say of value 1 Bitcoin. The transaction in which Alice obtained the Bitcoin is represented by the string T sub XA. So X is the public key of the owner of that Bitcoin, while A is the public key of Alice, the recipient of that Bitcoin. Suppose now that Alice wishes to give this coin to Bob, whose public key is capital B. This transaction is represented as the following string T sub AB. The string contains the hash of the previous transaction T sub XA in which Alice received the coin, Alice's public key, Bob's public key, the value of the coin, and Alice's signature using the private key corresponding to her public key, capital A. So the first public key is the public key of Alice, the owner of the coin, while the second public key is Bob's public key, Bob being the recipient of this Bitcoin. This transaction, which is an ECDSA signed message, is broadcast to the entire network on the peer-to-peer Bitcoin network. Bob and anyone else can verify the authenticity of the ECDSA signature by using the public key capital A, which again is the first public key in the signed message. Here's a transaction chain for the first Bitcoins. Recall that T0 is a genesis transaction where the first 50 Bitcoins were created and assigned to Satoshi, whose public key is capital S. T sub SA is a transaction whereby S gives Alice the 50 Bitcoins. More precisely, Satoshi gives the 50 Bitcoins to the entity whose ECDSA public key is capital A. The transaction TSA contains the public keys of S and A, the value of the transaction, the hash of the previous transaction, and S's signature on S, A, the 50 Bitcoins, and the previous hash. Similarly, T sub AB is a transaction whereby Alice gives Bob, the entity who owns the public key capital B, the 50 Bitcoins. When Bob receives this transaction, he can verify the signature using Alice's public key capital A. If the signature verifies, then Bob is convinced that Alice indeed has given the coin to Bob. The question is whether the coin is valid in the first place. Bob can verify this by using the validity of the transaction T sub SA, using Satoshi's public key S, to verify the signature on this message. And finally, checking that T0 is indeed the genesis transaction. Since the genesis transaction T0 is assumed to be authentic, and Bob verified the signature in TSA using Satoshi's public key, and verified the signature in TAB using Alice's public key, Bob is convinced that this transaction is valid. To spend these 50 Bitcoins, say to give them to Chris, Bob has to compose a similar transaction, TBC, and then sign the message with his private key, namely the private key little b corresponding to the public key capital B. The transactions in this chain are cryptographically linked by including the hash of the previous transaction in the next transaction. Note that the transactions contain Satoshi's, Alice's, and Bob's public keys, but not their names. This method of spending coins raises two questions. How can the recipient of a coin verify that it is not being double spent? without relying on a central third party. Also, how are new bitcoins generated? Suppose that Alice tries to spend her coin twice, in a transaction TAB with Bob and in a transaction TAC with Chris. Of course, only one of these transactions should be accepted as valid, and the other transaction should be rejected. Which one will be accepted and which will be rejected? To decide this, all valid transactions are stored in a public blockchain so that users and miners can decide whether a transaction is valid or not. So if a miner receives TAC and finds that TAB is already in the blockchain, then the miner will reject the transaction TAC because the coin has already been spent in the transaction TAB. Recall that all transactions are broadcast to all users via the Bitcoin peer-to-peer network. Any entity called a miner, whose public key is capital W, can volunteer to collect all transactions received since the last block was added to the blockchain. The miner verifies that these transactions are valid and that the corresponding coins have not been previously spent. Invalid transactions are discarded. The miner forms a block consisting of the hash of the previous block, the miner's public key capital W, a nonce, and the transactions T1 through Tn. The nonce is incremented until a hash value that begins with T0s is obtained. This block is then broadcast to the Bitcoin network. In this way, the Bitcoin blockchain is grown by another block. Users will accept the block if all transactions in the block are valid, if the coins have not been previously spent, and if the hash value begins with T0s. Note that any user who has a copy of the blockchain can check these things. Users show their acceptance of the block by growing the blockchain from that block. In other words, using its hash as a previous hash for the next block. So the blockchain serves as a public, decentralized ledger that records all transactions. There is a possibility that two blocks are created around the same time by two different users. Consider, for example, the case where Alice is trying to double spend her coin in a transaction with Bob, TAB, and also a transaction with Chris, TAC. These transactions are broadcast to the Bitcoin network by Bob and Chris. Some miners might receive TAB first and reject TAC, and the others might receive TAC first and reject TAB. And so some miners might create a block with TAB in it and not TAC, while some other miners might create a block with TAC in it but not TAB. Suppose also that the miners create these two blocks at around the same time. The miners would broadcast this block and this block to the Bitcoin network. Some miners might receive this block first, and they would grow the chain from that block, while some other miners might receive this block first, and then they would grow the chain from that block. This causes a fork in the Bitcoin blockchain. To remedy the fork, miners are programmed to trust the longer chain and continue to grow that chain. It is highly unlikely that the two chains will grow at the same rate, and so one chain eventually becomes longer than the other, and users will abandon the shorter chain and continue to grow the longer chain. The blocks that are not part of the longest chain are dropped and the valid transactions in them are returned to the miner's memory pool of unverified transactions. We can check now that the blockchain has the properties of being public, having consensus, liveliness, and persistence. It's clear why the blockchain is public. All the transactions in the blockchain are public knowledge, and anyone can download the blockchain from the Bitcoin peer-to-peer network. Miners agree to accept the block only if all the transactions in that block are valid. They also agree to grow the longest chain. And in this way, the blockchain achieves consensus. Anyone can broadcast a transaction to the Bitcoin network, provided that the transaction is valid and has a sufficiently high transaction fee, as we'll see later. It will be accepted and added to a block. This gives a block the property of liveliness. Finally, the blockchain has a property of persistence. Suppose that an entity wishes to modify a transaction, say TXY. This transaction occurred in the past. If the entity modifies even a single bit of TXY, then the block itself is modified, and thus its hash value also changes. With high probability, this hash value will not begin with T0s, and so the entity would need to compute a new nonce for that block, such that its hash value begins with T0s. This takes a bit of work. Now that the hash value of the block has changed, the entity needs to compute a new nonce for the next block, so that its hash begins with T0s, and so on. And so an entity who wishes to change a transaction that occurred in the past must generate valid proof of work for that block and for all subsequent blocks. This hashing will take a lot of time, and in the meantime, the rest of the Bitcoin miners will have grown the blockchain even further. Hence, it is very unlikely that an entity is able to modify any transactions that occurred in the past, unless that entity has more computing power than the rest of the Bitcoin miners combined. And this is why the blockchain has a property of persistence. To incentivize miners, the creator of a block, represented by public key W, is awarded R Bitcoins. Currently, R is 6.25. The reward incentivizes miners to do their work properly. In other words, verify that transactions are valid. Otherwise, they would expend significant resources on mining to produce a proof of work, but will not be able to collect the reward if users reject their block because it contained invalid transactions. The work factor T is automatically updated every 2016 blocks. This is done to ensure that the average time it takes to generate a block is 10 minutes. 2016 is a number of 10-minute segments in 2 weeks. Currently, the Bitcoin network is collectively generating hashes at the rate of approximately 2 to the power 67 per second, which translates to a work factor of roughly T equals 77. Now, a personal computer can do roughly 4 million hashes per second. So you can see that a single personal computer has virtually no chance of mining a block in 10 minutes. Instead, mining pools have been formed. These mining pools are massive mining farms, primarily located in China, but also in the US, Russia, Kazakhstan, and Iran. When a computer in a mining pool successfully solves the cryptographic proof of work challenge, all the miners in that pool share the reward. Here are a few security notes. If Alice gives Bob a coin, then Bob should only complete the transaction with Alice after he's convinced that the transaction TAB appears in the blockchain. And thus Alice is not double spending her coin. So Bob should wait until TAB appears in the blockchain, perhaps followed by several blocks. Currently, 6 is the recommended number. So you can see that Bitcoin transactions are not instantaneous. If Bob were to accept the transaction instantaneously, then Bob has to accept the risk that Alice might be double spending the coin. In that case, a miner might reject TAB, and so Bob does not end up with any Bitcoins. Since all transactions are included in the blockchain, which is public, payer anonymity and payment and traceability are not guaranteed. However, Alice can take some measures to increase the privacy of her transactions. It's difficult to give a precise and meaningful definition of Bitcoin security. However, informally, we can state that Bitcoin is secure as long as honest users collectively control more CPU power than any cooperating group of users, and therefore the honest users will grow the valid blockchain. I should note that Bitcoins can be combined and split. Here's an example. Suppose that Alice, represented by public key capital A, receives 25 Bitcoins from Bob in transactions TBA, and also received 20 Bitcoins from Chris in transaction TCA. So Alice has 45 Bitcoins assigned to her public key capital A. Suppose now that Alice wishes to give 30 of these Bitcoins to David, leave 14 Bitcoins to herself as change, and give 1 Bitcoin as a transaction fee. Such a transaction fee will be claimed by the miner who validates this transaction. The fee incentivizes miners to include transactions in the block they are mining. Here is a corresponding transaction. Alice forms the message with inputs the hashes of the 2 previous transactions, TBA and TCA. The message AD30BTC, which represents Alice giving David 30 Bitcoins. The message AA14BTC, which represents the message Alice leaving 14 Bitcoins as change to herself. These messages are hashed and signed using Alice's private key. Note that the sum of the Bitcoins in the inputs to the transaction is 45, whereas the sum of the Bitcoins in the outputs, this one here and this one here, is 44. The difference, 1 Bitcoin, is left as a transaction fee to the miner who includes this transaction in the block that it mines. Here is a more complicated example with multiple inputs and multiple outputs. I'm supposing in this example that Bob owns 2 public keys, capital B and capital H. So Bob is the only party who knows the corresponding private keys. I'll suppose that Bob received 9 Bitcoins in transactions T1 and T2. T1 had 3 outputs, 1 BTC from A to B, 3 from D to E, and 2 from C to H. So Bob is claiming this 1 Bitcoin and these 2 Bitcoins because Bob owns the public keys B and H. Similarly, T2 has 2 outputs in it, this transaction of 5 Bitcoins and this transaction of 6 Bitcoins. And Bob is claiming these 6 Bitcoins since Bob owns the public key B. I'll suppose now that Bob wishes to give 2.5 Bitcoins to F, 3 to I, 1.5 is changed to B itself, 1.75 is changed to H, and offer the remaining 0.25 Bitcoins to the miner who includes this transaction in the block it mines. So Bob now forms the transaction T3. T3 has 3 inputs, the first being the hash of T1 and the index 1, the 1 indicating that Bob is claiming ownership of the coin in the first output of T1. The second input is T1 tilde 3. So this is Bob claiming that he owns the Bitcoin in the third output of T1. And the third input is T2 tilde 2. Again, the second index 2 is Bob indicating ownership of the second of the outputs in T2. So the 3 inputs in total add up to 9 Bitcoins. 1 here, 2 here, and 6 here. The outputs are F2.5, I 3.0, B 1.5, and H 1.75. The 3 outputs add up to 8.75, the difference being the transaction fee to the miner who includes T3 in the block that it mines. Bob signs T3 3 times with the private key corresponding to the public keys B, H, and B, since these are the three public keys, including in the three outputs where Bob received his bitcoins. And so we see that Bob can combine bitcoins he receives in different transactions into one big coin, and then use that coin to pay other people while keeping the change for himself. So Bitcoin is divisible. Bitcoin users have to be very careful to protect their ECDSA private keys. If an attacker learns Alice's ECDSA private key a, then the attacker can spend all the coins associated with the ECDSA public key A. Similarly, if Alice accidentally deletes or loses her private key, then all coins associated to the public key A are lost forever. No one can ever spend these bitcoins. Indeed, it is estimated that about 20% of all bitcoins that have been created have been lost forever. To protect her bitcoins, Alice could store them at an exchange, but that brings considerable risk. Mt. Gox, a Bitcoin exchange based in Tokyo, lost 850,000 customer bitcoins and declared bankruptcy in 2014. Later, it found 200,000 of these bitcoins. In early December 2018, the founder of Canadian cryptocurrency exchange Waterloo CX died. Apparently, he was the only person who knew the password to access $190 million worth of customer cryptocurrencies, including Bitcoin. Instead of using an exchange to store her bitcoins, Alice could use a hardware wallet such as Ledger, or a cosigner service such as BitGo, or store funds at a custody service such as Anchorage Digital. My description of Bitcoin has omitted several technical details. First, the public key is actually identified by its 160-bit hash value called an address. The block has a header which contains the root of a so-called Merkle tree, where the transactions are stored. Storing the root of the Merkle tree in the blockchain header provides data integrity for all the transactions. The block header is about 80 bytes in length, while the size of the block itself is about 1 megabyte. The 1 megabyte limit means that a block can have at most 4,000 transactions in it. The use of Merkle trees enable simplified payment verification, known as SPV. Here, a lightweight client only needs to download the relevant block headers and some other data to verify that a transaction is included in the Bitcoin blockchain. The client does not need to download the entire blockchain. In the next video, we'll discuss some shortcomings with Bitcoin and how they are being addressed.